Okay, so this is our GUI. You can choose an image folder. You can adjust the quality. So once we read in the images, they're being stored in our data structure. Boom, done. Okay, now you have to save it as some sort of video file. We made our little demo.folder here. We call it compression.ping. Image read and saved. That was fast. So this is the original file size of all the images added together. And bam! We reduced that to 43 megabytes. That's right, 43 megabytes. Smiley face, smiley face, smiley face. Bam! Smiley face. Now let's play the video. So we're going to browse for our file. Read that file in. The decoder is working. Oh, it's done. Whoa. Now the video is playing. Here you can see our real-time video effects. Heat map is one of my favorites. It's pretty spectacular. And we're done.
Our challenge is to design and implement an efficient decoder of multiple images into a single video file and to play that video file on demand. For this project, there were 7 requirements levied on us. The first was to encode up to 100 images in under 5 minutes. The second was to produce a video file size that is less than the sum of the individual files. The third was to play back the video at greater than or equal to 10 frames per second. The fourth was to create a GUI for ease of use. The fifth was to create Android and PC clients for the video viewer. The sixth was to support the multiple image formats, PNG, GIF, JPEG, BMP, and WBMP. And the seventh was to include real-time video effects during video playback. Now I will go over the system architecture. To start our system process, we input the image, and then we convert the RGB image to YCRCB. Then we compute the DCT of the image to get the high-frequency values. After we remove the high-frequency values, we use the IDCT to convert the DCT coefficients to YCRCB values. We then use interframe compression to further compress the data into its IPPP frame structure. Then we use chroma subsampling to get rid of the CR and CB values. Once we have the data ready to save, we use a bit stream generator to save the compressed data to a video file. On the decoder side, we read in the bitstream and convert the bitstream data back to the original macro blocks. Then we convert the YCRCB values to RGB. Then we reconstruct the original images from these values. From this point, we then play a video based on the images we loaded in from the compressed video file. If we start at the bottom of the figure of the overall data structure, for ease of processing, we divide each frame uniformly to 8x8 blocks of pixels. Since each pixel is represented by a Y, CR, and CB value, we use a 3x2D arrays to represent a single block. Notice that the figure shows the CR and CB arrays as 4x4 rather than 8x8. This shall be explained further in this video. All the blocks of a frame are saved in an array to represent a single frame. Similarly, all of the frames are saved in an array. We took advantage of the requirement of considering a maximum of 100 images for the project, and it decided to save all of the frames in a single array. The same data structure is modified in place by all the methods used in the project, giving constant access operation times and constant searching operation times available for all methods. Another method we use for compression is chroma subsampling. The idea behind this is that it turns out the human visual system is less sensitive to motion of color compared to luminance. That is why we convert to the YCRCB scheme. This separates the luminance values in Y and to color components in CR and CB. There are different schemes for subsampling. We use the 4:2:0 method, shown here, in which, given this 2D array of pixels on the left, we only select the indices shown on the right, in blue. In our case, we had 8x8 blocks that were reduced to 4x4 blocks, thereby compressing the image size. We start the interframe compression process by dividing all the input frames into groups of pictures. This figure shows a group of 4 frames transmitted from left to right. The idea is that the first picture in the group of pictures, or GOP, what we call the I frame, will be transmitted fully, and each other frame will only be sent partially. To achieve this, each P frame block will be compared to the initial I frame block in the same pixel location. In other words, this block in the P frame will be compared to this block in the I frame, and so on. Each comparison of blocks will involve finding the absolute difference between all the pixels and adding them up. If the value is less than a certain threshold, then those two blocks will be counted as similar. In other words, say if this block at the top left in a P frame is similar to this block at the top left of the I frame, then instead of transmitting this block in the P frame, a flag will be set that will act as a reference to the block in this I frame. In our case, we changed the value of the first pixel to a fixed value, which acted as our flag. which when read by the decoder, it knows to copy the values of the block in the iframe of the current GOP being decoded. The time complexity analysis for the interframe compression function, we loop through all the frames. Therefore, we have big O n time complexity, where n is the number of frames. We must consider that every frame is composed of smaller blocks. Each block comparison operation is done in constant time, but the number of blocks is dependent on the number of pixels in the frame, which is p. Since we loop through all the blocks, this will result in a big O p time complexity. Combining these two values, we get a worst case time complexity of big O n times p. We wrote a function that calculates the two-dimensional discrete cosine transform for the purpose of performing a lossy compression with quantization. Our function instantiated the DCT cosine coefficients, then multiplied those coefficients to the matrix. We did this by first calculating the matrix of cosine coefficients and multiplying the original function by the matrix. Then we transposed our cosine coefficient matrix and multiplied the original matrix by it again. The two-dimensional DCT is limited to 64 pixels, which, in terms of computation, can be considered constant time. Because we are looping through this for all frames, the time complexity becomes big O n times p, where n is the number of frames and p is the number of pixels. For the bit stream compression function, we took the data structure that contained our image data and added those values as bytes to a text file. For every group of pictures, we stored the entirety of the iframe. For the p frame, if the pre-frame matched the iframe, then we would ignore those blocks in the p frame, and within the bit stream, we would put a pointer from the p frame to the blocks in the iframe that the p frame matched. In our bit stream, if a p-frame had a 0 in front of it, then it did not match the iframe. If the p-frame had a 1, then it matched the iframe, and immediately following the 1, we would put our pointer to the block in the iframe. The time complexity for this bitstream compression function was theta p to the n, where we are working with every single pixel within all of our frames. Thus, p is the number of pixels per frame, and n is the number of pixels. Along with the data from the data struct, we added a header to our bitstream. The header had exactly 10 bytes of information, the first 2 bytes being the number of blocks in each frame. The next piece of information was a group of pictures, which was a measure of how many p-frames to an iframe. For a group of picture of 4, we had 3 p-frames to an iframe. For the height, we reserved 2 bytes, and for the width, we reserved 2 bytes. The frames per second was hard-coded to 10, but we reserved 1 byte of information with the assumption that this could be changed later. The number of frames was saved as a 2-byte value. This meant we could have anywhere between 1 and 65,536 frames. For the actual data, each pixel value was a byte. The reference value, 0 or 1 flags that said if the p value was similar to an I value, was exactly 1 byte, and the pointer to the iframe was 2 bytes. On the decoder side, the overall working structure of the decoder is as follows. The input for the decoder is a compressed video.txt file. The decoder uses index processing to differentiate and process the blocks in the stream. The decoder first checks if current frame is an I or P frame, after which it converts each pixel in the macro block to its RGB values. For each iframe, each macro block contains Y, CR, and CB values, with lengths fixed of 64, 16, and 16. Thus, each macro block in an iframe is 96 bytes long, which is 96 times 8 bits. Now let's go over the structure of the P frame. Each macro block in the P frame has an indicator byte attached to it. If the indicator byte is a 0, then the macro block doesn't match any stored macro blocks in the iframe. Thus, the size of this macro block would be 96 bytes. A 1 before a macro block indicates that this is a matching macro block. For this type of macro block, the second value indicates the reference pointer. Thus, the size of each macro block in a P frame is either 96 bytes or 3 bytes. For our results, we were able to complete 6 of our requirements. We partially completed requirement 2. The video file size has to be less than the sum of individual files. For each of our test sets, we had an approximate 2/3 compression ratio. The set of images provided by the professor gave us an encoded file size larger than the sum of the original images. Thus, we claim that it is conditionally complete. So now we're going to show you the Android client. Oh, it's minus 14 in Beijing. So we're loading the app. Yes, we're going to allow it. Give me all your permissions. So we're going to click on the play button here very shortly. As you can see, we need to select a file. So we're going to open that up, select the parent folder, get our video file. Boom. Now it's loading in there. Now we're going to click play. Bam. There it is. That's our video. So we're going to play around with some of the effects. Cool. It's pretty awesome. Wow, what's that? That's psychedelic. It's pretty spectacular. Thanks for watching.